Hello, and welcome to this online lecture. My name is Patty Kokish, and today we are doing a final exam review for Online Math 136. So congratulations for making it this far. You just have a final exam review due, and then your actual final exam, which you'll have to go to your proctoring site in order to take. So I picked many of the questions that were on your final exam review homework, and I've put some similar exercises into this presentation. These are all pulled from previous presentations we've done, but it kind of wraps together all of the different concepts and shows you a bunch of different examples so you can kind of remind yourself of what you were doing a few weeks ago. Please note that there is a final exam formula sheet that is posted. It should be in Blackboard for you guys. I don't remember if it's under final exam review homework or which is session 15 or session 16, which is the actual final exam. But you should be able to access that, and then when you go to your proctoring site, that should be available to you. So let's go ahead and get started. So let's look at an example like this where we're finding a polynomial function from its zeros. So let's say we want to find a polynomial whose degree is 3, who has zeros of -4, -2, and +3. Now, if you recall, the degree is just the highest power of x that you have as part of your polynomial. Now, you also have to remember what zeros are. So if you think about zeros and how they're related to factors, if you recall, if -4 is a 0, that means that x plus 4 has to be a factor. If -2 is a 0, then x plus 2 has to be a factor. It's always the opposite sign. And then if 3 is a 0, that means that x minus 3 has to be a factor. So really all we have to do is we have to create an f of x equal to a, we're going to talk about what this is in a minute, times x plus 4, that's the factor for -4, x plus 2, which is the factor for -2, and x minus 3, which is the factor for +3. And what happened is we went ahead and multiplied this out. We didn't show all of the steps. Make sure you pay attention to what MyMathLab wants. If it's okay with you leaving it in factored form, then just leave it just like this, okay? And if it wants it actually multiplied out, then you're gonna have to do that. Now, in order to do this, you have to do it very carefully. I would just do it 2 at a time. So take these first 2 and do FOIL. You'll get x squared plus 6x plus 8. And then what you'll do is you'll distribute an x to each of those. You'll distribute a -3 to each of those. And then you will go ahead and combine any like terms that you might have. And you will end up with x cubed plus 3x squared minus 10x minus 24. Now, a can be any real number. So you could let it be a 2, a 5, a negative number. It doesn't really matter. But the easiest thing to do is to just let a equal 1. So on the actual assignment, what you're going to want to do is you're not going to include this at all. 1 times anything is just the same thing that you started with, so you don't need anything there at all. So your answer would just be x cubed plus 3x squared minus 10x minus 24. Now, especially for your exam, I want to point out a way that you can check this to make sure that you did everything correctly. And the easiest thing to do is first make sure that the polynomial has the correct degree. So if we look at this polynomial, we definitely have x cubed, so that means we have a degree of 3. And then for the -4 and the -2 and the 3, what we can do is we can plug those numbers into our calculator, and we can make sure that our y, or our f of x, ends up being 0. So if you do -4 to the 3rd power, make sure you put parentheses around that, plus 3 times -4 squared, make sure that you have parentheses around your -4 again, minus 10 times -4, minus 24. If you do all of that, you end up with 0. So we get y equals 0, which is exactly what we want. You would want to do the same thing with -2 and +3. If these all work, then chances are that you found the correct polynomial. Okay, now I want to go through this slide, which gives a summary of finding horizontal or oblique asymptotes of a rational function. So n is going to be the degree of the numerator, m is going to be the degree of the denominator. If n is smaller than m, meaning that the degree of the numerator is less than the degree of the denominator, then r is already proper, okay? And the graph will have a horizontal asymptote of y equals 0, the x-axis. So if the degree of the numerator is smaller than the degree of the denominator, then y equals 0 is your horizontal asymptote. Now, if n is greater than or equal to m, then r is called improper, so we use long division. Now, one thing to notice is that if they're the same, if n is equal to m, all you have to do is you have to look at this first term, okay, so the highest term for each, and by highest I mean the one with the highest power attached. So you look at these right here, okay, and you just take the ratio of those two. So you take an divided by bm, and then y equals whatever that number, that's your horizontal asymptote. Now, if n is equal to m plus 1, meaning that the degree of the numerator is 1 more than the degree of the denominator, then the quotient obtained is in the form ax plus b. So it's some polynomial of degree 1, and the line y equals ax plus b is an oblique asymptote. If n is greater than or equal to m plus 2, meaning that the degree of the numerator is 2 or more larger than the degree of the denominator, then the quotient obtained is a polynomial of degree 2 or higher, and we say that it neither has a horizontal nor an oblique asymptote. And in this case, for very large values of x, or absolute value of x, the graph is going to behave like the graph of the quotient. So let's say we want to find the horizontal or oblique asymptotes, if any, of the following graph. R of x equals 8x squared minus x plus 2 divided by 4x squared minus 1. So if you look at this, whenever you see horizontal asymptotes, you always want to make sure you pay attention to the degree of the numerator, degree of the denominator. In this case, the degree of our numerator is 2 because we have an x squared. Degree of denominator is also 2. So all we have to do is just take y equals 8, which is the number in front of our x squared up here, divided by 4, which is the number in front of our x squared down here. 8 divided by 4, as you know, is 2, so y equals 2 is our horizontal asymptote. This works anytime the degree of the numerator and the denominator are the same. You just look at the first terms. First term of the numerator, first term of the denominator, and then divide. Okay, now we have a whole list of steps for analyzing the graph of a rational function. So these are really important steps to be familiar with. Step 1 is to factor the numerator and the denominator of r and then find the domain of the rational function. Step 2 is going to be to write r in lowest terms. Step 3 is going to locate any intercepts on the graph. So x-intercepts, those are going to be the zeros of the numerator. So if you're trying to find x-intercepts, you just have to set your numerator equal to 0 and then solve. And y-intercepts are going to be the value when x is 0. Step 4 is to determine vertical asymptotes. So make sure that you remember what vertical asymptotes are. We're going to go through an example in a minute, but those are the places that give you issues with your denominator after you've simplified. Horizontal asymptotes we just talked about in pretty good detail, and we did an example. Step 6 is to use the zeros of the numerator and the denominator to divide the x-axis into intervals, and then determine whether it's positive or negative, get a couple extra points, and then you can graph. And then you can analyze the behavior of the graph near each asymptote and indicate the behavior, but after you've done steps 1 through 6, it should be enough to graph. Okay, so let's do the following steps, so the ones that we just looked at for the graph r of x equals x minus 1 over x squared minus 4. So step 1 is to go ahead and factor the numerator and the denominator, and then find the domain. So if we factor our numerator, well, there's nothing to do with it. It's just x minus 1, we can't factor that. But our denominator is the difference of two perfect squares, so it ends up being x plus 2 times x minus 2. If there was anything to cancel, we would do it at this point, but we go ahead and state the domain. So domain is going to be all x's such that x is not equal to negative 2 and x is not equal to 2. The other way that you could write this would be interval notation. You would have from negative infinity to negative 2, from negative 2 to 2, and from 2 to infinity. You want to go ahead and write r in lowest terms. So if there's anything that would cancel, then you can go ahead and cancel it, like if we had an x minus 2 up top or something like that. But there's really nothing to cancel here, so r is already in lowest terms. It is important to note, though, if we had canceled, that would mean that we would end up with a hole in our graph. Step 3 is to locate the intercepts of the graph, determine the behavior of the graph near each x-intercept using the same procedure as for the polynomial functions, plot each x-intercept, and indicate the behavior of the graph near it. So since 0 is in the domain of r, the y-intercept is going to be r of 0, which is equal to 1/4. So if we plug 0 in for x, we get -1 divided by 0 plus 2, which is 2, times 0 minus 2, which is -4. So we have -1 over -4, which is positive 1/4. So that's our y-intercept. X-intercepts are going to be the places where our numerator is 0. So if we set x minus 1 equal to 0 and we solve, we get x equals 1. So that's our only x-intercept. We can have more than one, but in this case, we only have one. Now, near 1, what we do is we just plug 1 in for our denominator x's. So we have x minus 1 over 1 plus 2 times 1 minus 2, which is going to be -1/3 times x minus 1. So it's going to look like a line with a negative slope there. Step 4, we want to locate the vertical asymptotes and then graph each of them using a dotted line. So vertical asymptotes are where the denominator is 0. So we already figured this out from the domain. Again, it's important to note that we've talked about in previous sessions that domain exclusions and vertical asymptotes are not always exactly the same because of the fact that you can have holes. But we don't have any holes in this case, so the numbers that we exclude from our domain are the same as our vertical asymptotes. So the numbers that we excluded from our domain were -2 and +2 because they make our denominator 0. So x equals -2 and x equals 2 are our two vertical asymptotes. We then want to locate the horizontal asymptote, or oblique if one exists, and then determine any points at which r intersects the asymptote. Now, in this case, the degree of the numerator is less than the degree of the denominator. Okay, so that means that the line y equals 0 is a horizontal asymptote. In order to determine if the graph intersects the horizontal asymptote, we have to solve the equation r of x equals 0. And we do know that it's already going to be our x-intercept, which is 1. Step 6 is to use the zeros of the numerator and the denominator to divide our x-axis into intervals, determine whether it's above and below, and plot some extra points. So if you look here, I would go ahead and label, they don't have it labeled here, but I'd go ahead and label your -infinity and your infinity. And then you have these intervals, you've broken it up. -2 is a 0 of your denominator, 2 is a 0 of your denominator, and 1 is a 0 of your numerator. And then you break it up into intervals from -infinity to -2, -2 to 1, 1 to 2, and 2 to infinity. And then you just need to pick a number that's in that interval. So you can pick anything you'd like, try to be nice, since you have to solve it, but go ahead and take, I don't know, -3 in this interval. 0 is always a good option if you can choose it. 3/2, you're kind of stuck with a not so nice one between 1 and 2, and 3. So all you have to do is just plug those values in for x, okay, and you're just going to get some answer. It's not necessary that it's exact, okay. You're looking for an approximate, and really what is most important is that you know whether it's positive or negative. Now in this case, it's -0.8 if we plug -3 in for x, 1/4 if we plug 0 in for x, -2/7 if we plug 3/2 in for x, and 0.4 if we plug 3 in for x. So since we have a couple of negative values here, that means that those intervals, we're going to be below our x-axis. Anywhere that we have a positive value, that means we're going to be above our x-axis. And then they're written here as coordinates as well. So if we move to the next page, this is made slightly smaller, but it's the same from the previous slide. You'll see we have x equals -2 and x equals 2 drawn in with dotted lines, as well as y equals 0. Those are all of our asymptotes. You'll also see that we have our x-intercept of 1 and our y-intercept of 1/4. And then there are also some additional points on here. 3/2, -2/7, 3, 0.4, and -3, -0.8. And what you can see from actually graphing some of this stuff is that these are going to connect. You're going to have this piece over here that approaches your asymptotes, a piece up here that approaches your asymptotes, and something that looks kind of like a -x³ up here in the middle. So here's your final example. If you're ever not sure exactly how to connect your lines, okay, so you have all of this information and it's still not looking exactly how you want, you can always plug in some extra values for x, figure out what y is, and then graph them from there. So let's say you wanted to know, does this open back down or does it go up? If you pick -1 for x, then you'll be able to see that you have a value over here and that it should connect this way. And in addition, you can pick some extra values here to kind of confirm that these are correct. Okay, let's do something a little different. This is solving a rational inequality algebraically. So when we did these as part of this chapter, when we had inequalities, we did polynomials and rational expressions. Polynomials, we just found the zeros, put them on a number line, and evaluated. Or we can graph. Okay, the same is true with rational inequalities. So you can either graph the function and then look at the graph to tell, or you can do it algebraically. I always suggest to my students to do it algebraically because it's just one less graph that you have to construct. Graphs are time consuming and they tend to be confusing for students. So I think the algebraic way is the best. So let's solve this inequality. We have 4x plus 5 over x plus 2 is greater than or equal to 3. Now this one is quite confusing because we don't have a 0 on the right-hand side. Typically when we're solving these, it's a little nicer than this actually. Normally we're given it already greater than or equal to 0, less than or equal to 0, but this one's kind of one where you have to use your brain a little more. It's greater than or equal to 3. Before we solve any inequalities though, we have to set it so that the function f is on the left side and 0 is on the right. So what we need to do first is just subtract 3 from both sides. So we have 4x plus 5 over x plus 2 minus 3 is greater than or equal to 0. And then what you need to do is remember some stuff about rational equations, okay? And we need to get a common denominator. So here we multiply our -3 by x plus 2 over x plus 2. And then from there, we've created a common denominator of x plus 2. We distribute. You have to make sure you distribute the negative along with the 3. So when you distribute that part, it ends up being -3x minus 6. Combine like terms. So it's x minus 1 over x plus 2 is greater than or equal to 0. Now, this certainly could be given as your original equation instead of this one right here. With this top one, the one that we were given, it just involved a little bit more work. But if you're given this right here, then you're just going to start from this step. So step 2 is to determine the real zeros of f and the real zeros for which f is undefined. So really you're finding the zeros of the numerator and the zeros of the denominator. So if you look at this, the 0 of your numerator is just going to be 1 because if you plug 1 in for x, you get 0. The 0 of the denominator is going to be -2. That's where your function is undefined. Then we use the zeros and the undefined values. So we use the 0 of the numerator, 0 of the denominator, in order to divide a real number line into intervals. So in this case, we have from -infinity up to -2, -2 to 1, and 1 to infinity. And these are shown here as well. We pick a number in each of the intervals. Any number that's in the interval, just have to make sure it's actually in there. And then you plug it into your equation and you determine if it's positive or negative. Now, it's important that you plug it into the equation when you already had a 0 on the right-hand side, okay? You don't want to plug it into the original. Plug it in where you had a 0. So if we plug -3 in, we get 4, which is positive. If we plug 0 in, we get -1/2, which is negative. And if we plug 2 in, we get 1/4, which is positive. Now, it's also important that you keep in mind, do you want positive or negative answers? And that's given by the original setup of the question. In our case, we had greater than or equal to. That means we would want positive values. So if we look, we're just going to take the positive pieces here. So we're going to take our interval from -infinity to -2, and we're going to put a union symbol and take it from 1 to infinity. Now, this one is a very particular one, which is quite a bit more difficult. We have to think about it a little bit because we don't just have greater than 0, we have greater than or equal to 0. So if we take 1 and we actually plug it into our equation, we do get 0. And 0 is in fact greater than or equal to 0. So we need to put a 1 with a bracket next to it. Now, -2 is another story because if we plug -2 in for x, we get a 0 in our denominator. Now, we know that we cannot have zeros in our denominator, so we would never put a bracket by -2 because we would never want to include it. Make sure you pay attention to whether we want set builder notation, which would be x, such that x is less than -2 or x is greater than or equal to 1, or if you want interval notation, which is going to be from -infinity to -2, union 1 to infinity, where 1 is inclusive. And if you're asked to sketch the solution set, make sure that you have brackets by anything that's included, parentheses, or open dots by anything that is not included, and then you shade the appropriate directions. Okay, here is listed a summary of the graph of a polynomial function. So it's important to remember a few things about polynomials. The first being that the degree is going to be n, that's your largest power for your polynomial. Graphs of polynomials are always going to be smooth and continuous. The maximum number of turning points is always one less than the degree. Even multiplicity means that the graph touches the x-axis at that point. Now, multiplicity is the power that's attached to that zero, okay? So if that's an even number, then it touches. If it's an odd number, then it crosses. Between zeros, the graph is either stuck above or below the axis. It can't change unless you have a zero there. And then the end behavior is going to look like your very first term. So let's look at this graph here. We have f of x equals 2x plus 1 times x minus 3 squared. So the first thing we want to do is go ahead and determine the end behavior. Now, you don't have to multiply this all the way out, but it is important to think about what would you get if you actually did multiply this all the way out. Now, in this scenario, they did go ahead and FOIL everything, but I would suggest that you really don't have to do that. If you imagine yourself taking 2x and multiplying by x squared, you should end up with 2x cubed as your very first term. Okay, now we don't really care about the rest of this simplified version, but what we do care about is the degree, which is going to be 3 because we have a 2x cubed term. And we do care what the end behavior looks like, which in our case is going to be this first term, which is 2x cubed. So that means that the graph of f behaves like 2x cubed for large values of absolute value of x. Then we want to find the x and the y intercepts and graph the function. Of the graph of the function. We're going to graph a little later. Y-intercept, we just set x equal to 0. So we should get 0 plus 1, which is just 1, times 0 minus 3 squared, which is 9, so just 9. To find the x-intercepts, we solve f of x equal to 0. So we set our whole right-hand side equal to 0. And we should get two solutions. We break it into two parts using the zero product property. And we end up with x equals negative 1/2 and x equals 3. So the x-intercepts are negative 1/2 and 3. Now we determine the zeros, which is just another word for x-intercepts, and find their multiplicity. So we know that negative 1/2 is a 0. If we look at where negative 1/2 comes from, it comes from this part right here. If you look at the multiplicity, that's just the power. It's just going to be a power of 1, so it has a multiplicity of 1. Since 1 is an odd number, the graph is going to go ahead and cross there. But at 3, which comes from this piece right here, we have a multiplicity of 2 since the power is 2, which is an even number, which tells us that the graph is going to touch at 3. The maximum number of turning points is always going to be 1 less than the degree. We know that our degree is 3, so the maximum number of turning points is going to be 2. Determining the behavior of the graph near each x-intercept, I'm going to skip through this. This isn't so important, okay? This helps get a very nice graph, but you don't have to be this precise, so I'm just going to skip through this. Step 6 is to go ahead and put everything together. So we know that negative 1/2 is a 0, we know that 3 is a 0, and we know that 0, 9 is a y-intercept. We also know that the end behavior is going to look like 2x cubed. Now, if you recall, x cubed is kind of that elongated S shape. 2x cubed is just going to be a stretched out version of that, which does not change at the ends. So if you look at what our graph is going to look like, it's going to go down on the left, up on the right. And then you just need to pay attention to whether it's crossing or touching. So at 3, it should just cross our graph. So it kind of touches at the 3 and then comes right back up. Or sorry, it touches, not crosses. So it touches at the 3, comes right back up. And then at negative 1/2, it actually crosses. So it goes through the x-axis. Okay, let's review this. This is the conjugate pairs theorem. So let's say we have a polynomial of degree 5 whose coefficients are real numbers. And so far we have 3 of the zeros, negative 2, negative 3i, and 2 plus 4i. And let's say we want to find the remaining 2 zeros. As long as you remember the conjugate pairs theorem, this is a very easy problem. Since f has coefficients that are real numbers, complex zeros appear as conjugate pairs, so they come in doubles. That means that if we have a negative 3i, that we should also have a positive 3i, which is the conjugate, as a remaining zero. And since we have 2 plus 4i as one of our zeros, 2 minus 4i is going to be the other kind of paired zero. Okay, let's take a look at evaluating a composite function. Okay, so let's say we have f of x equals 2x squared plus 3, and g of x equals 4x cubed plus 1. And we're just going to go through a and b. Okay, so let's say we want to find f of g of 1 and g of f of 1. So f of g of 1 means that we take g of 1 and we plug it in for f. So g of 1, if we take this, we have 4x cubed plus 1. We take a 1, we plug it in for x. 4 times 1 cubed is just going to be 4. 4 plus 1 is 5. And then we take that and we plug that in to f. So we have 2 times 5 squared plus 3, which is going to give us 53. G of f of 1 means that you're going to find f of 1. So we're going to plug 1 in for x. So 2 times 1 squared plus 3, that gives us 5. And then we plug 5 in for x into g. So we have 4 times 5 cubed plus 1, which is 501. Now, it's important to remember that we use these when we're verifying inverses. So we could have g of f of x or f of g of x when you have two functions that are inverses of one another. If you recall, g of f of x and f of g of x should both end up being x. And I'm just going to click through C and D. These are very similar. Okay, let's say we have a graph like this where we have some points, -2, -1, -1, 0, 2, 1. This is kind of a piecewise graph where it changes slope. And let's say we want to draw the inverse. Now, if you recall, there is a very easy way to do this, a couple of easy ways actually. One of them is to draw the line y equals x, which is basically just forms a 45-degree angle with your x-axis and your y-axis. And then just flip it around that, okay? But the other way to do that, if it's a little hard to see how this works, what you can do is just reverse the coordinates. So instead of 2, 1, we really have 1, 2. So that's the point on our new pink graph. Instead of having -1, 0, we now have 0, -1. So that's a point on our pink graph as well. And instead of having -2, -1, we have -1, -2. And then we just connect our lines. Make sure that anywhere that our original line, hit the equation y equals x, our new graph should hit there as well. Okay, let's take a look at solving some exponential equations. So we're going to start with a couple that hopefully are kind of easy. It's important to remember that if you get something where you have the same base, so a to the u power equals a to the v power, then you just ignore the bases and just keep the exponents so that you have u equals v. So for a here, we have 2 to the 3x minus 1 equals 32. Anytime you can go ahead and rewrite this so that they have the same bases, you want to go ahead and do that. So in this case, we're going to rewrite 32 as 2 to the 5th. Since we have the same base, we just ignore the base and keep the exponent. So we have 3x minus 1 equals 5. Add 1, divide by 3, and we get x equals 2. These are always really easy to check to see if you got them right. Just plug 2 in for x and make sure that it works. Use your calculator to kind of confirm that. In this case, we just get 2 to the 5th equals 32, which is in fact true. This one over here, we need to remember a couple of things. First of all, if you have a power to a power, those two things are going to be multiplied. So we rewrite this as e to the -4x, this piece on the right. So we have e to the -4x over e to the 3x. Now the other thing you need to remember is that when you're dividing, that's just like subtracting. So if you have the same bases here, you can subtract the exponents. And we know that -4x minus 3x is going to be -7x. So really what we have is e to the 2x minus 1 equals e to the -7x. Now, I always like to tell my students, don't be afraid when you see e. E is just a number. It's not a very nice number, but it's just a number. So since they're the same bases, so we have e's and e's on both sides, we just ignore the e and keep our exponents, just like the last one. So we have 2x minus 1 equals -7x. Subtract 2x from both sides and divide by -9. So we get x equals 1/9. And again, you can check this in your calculator. This one you're going to have to be a little more precise with. Be very careful when you're plugging it in, but it will work. Okay, here I have listed a summary of the properties of logarithms. Make sure you consult with your formula sheet so that you know what is provided, what is not. It's important to remember these though. Particularly, it's very important that you know the relationship between logs and exponents, okay? So log form and exponential form. You will have to change back and forth from those several times when you're either solving equations or when you're asked to do so. A couple of the other important ones, this one over here. If you have an exponent, you can always take that out front, okay? That's a good one to know. Also, if you're multiplying, you can turn it into addition if you separate them into two separate logs. Division, you can separate into subtraction. And then it's important to know the change of base formula as well. So log base A of m is going to be log base B of m divided by log base B of A. You can use any base you want. Typically, students will use either base 10, which is what their calculator does automatically, or ln, which is log base E. And then this one kind of goes right along with our exponential formula that we just, or equation that we just looked at, where if we have the same base, so if we have log base A and log base A, you can just ignore the logs so that you're just left with whatever you were taking log of. Okay, so let's change a couple of exponential statements into logarithmic statements. This should be kind of a no-brainer at this point, so you should be able to do this basically in your sleep, all right? So if we have 1.2 cubed equals m, that's going to be the same thing as saying 3 equals log base 1.2 of m. So 1.2 is our base, so it's still our base here. Our exponent is now by itself. Same kind of thing here. We have an exponent by itself, so we have b equals log base e of 9. Another way to write that would be ln. And then for this one here, we have 4, that was our exponent, equals log base a, base of 24. All right, using the change of base formula. So let's say we want to approximate log base 5 of 89. Most of you have calculators that probably will not do this for you, so you need to know the change of base formula. So all you have to do is just take log of 89 and divide it by log of 5. The other option you have is to use ln of 89 and ln of 5. You cannot mix and match these, okay? You either have to use log for both or ln for both. You will not get the correct solution if you mix and match. But either way that you do that, you should get somewhere around 2.8. And what that's saying is that 5 raised to the 2.8 power is going to be somewhere around 89. And you can confirm that in your calculator as well. I'm going to just skip through B. It's the same thing, it just has nastier numbers. All right, let's look at an example where we have to write a logarithmic expression as the sum of logarithms. So let's say we're given something like this, log base 2 of x squared times the cube root of x minus 1, and it tells us that x is greater than 1, and we want to write it as the sum of logarithms. Express all powers as factors. So anywhere we have a power, we want to write it as a factor. So the first thing that we notice is that we do have multiplication. We have x squared times cube root of x minus 1. So the first thing that we do is we split that up into two separate logarithms. Log base 2 of x squared plus log base 2 of cube root of x minus 1. And then what you want to do is you want to think about cube root and an alternate way that you could write that. Now if you recall, if you have cube root, square root, fourth root, whatever it may be, you can always write it as a power. So you always do 1 divided by whatever the root is. So in this case, we have the 1/3 power. So we have log base 2 of x squared plus log base 2 of x minus 1 raised to the 1/3 power. And then we just bring our powers out front because they asked us to express all powers as factors. So we take our 2 that was attached to our x for x squared and we bring it out front. And we take our 1/3, which was originally our cube root, and we bring that out front as well. All right, let's do one where we have division. So let's say we have log base 6 of the quantity x to the 4th divided by x squared plus 3 squared. X is not equal to 0, and we're going to write that as a difference of logarithms. So the first thing that you should notice is that we definitely have division here, so we're going to change that into subtraction. So we have log base 6 of x to the 4th, that was our numerator, minus log base 6 of x squared plus 3 squared. And then we still want to write all powers as factors. So we want to go ahead and break this out so that we have x to the fourth is now written as 4 times log base 6 of x minus 2 times log base 6 of x squared plus 3. And I want to point out that these can be difficult for students to see like when you're done with it, but what you want to look for is anywhere where you have like a power where everything is raised to that power, you always want to write that out front. And then you always want to look for any multiplication or division that's done within the log so that you could separate that into either addition or subtraction. Okay, let's do one other that just gets uglier and uglier. First thing you should see here is that we have division. So we want to change it into subtraction. So first we have ln of x cubed times the square root of x minus 2 minus ln of x plus 1 squared. So all we've done is we put our numerator in one natural log, our denominator in the other, and we've subtracted. And then you should notice that within the numerator itself, there is multiplication, so you can split that up as well. So you have ln of x cubed plus ln of x minus 2 to the 1/2 power minus ln of x plus 1 squared. Now you'll also notice in this step that they rewrote x minus 2 to the 1/2 power from the square root of x minus 2. It's always important to rewrite roots as powers so that we can express them as factors. So we just bring those factors out front now. So we have 3 times ln of x plus 1/2 times ln of x minus 2 times ln of x plus 1. Now we don't have any multiplication left within our ln's, no division, and no powers, so that means we're done. Okay, now these are going in the opposite direction. So let's say we're given kind of a long expanded logarithm and we want to write it as a single logarithm. Now in this case, you want to go back and you want to write numbers that have been expressed as factors back as powers, okay? Anything that was addition, you want to change back into multiplication. Anything that was subtraction, you want to change back into division. So let's say we have this, 3 times ln of 2 plus ln of x squared. So in this case, we take our 3 and we move it back up to the exponent. And then we also should note that 2 cubed is just 8, okay, so we can just write that as ln of 8. Now we notice we have addition here, so that changes into multiplication. So we have ln of 8x squared. All right, this one down here, we want to rewrite anything that's out front as a power. So this 1/2 becomes a power, this 2 becomes a power. And then what we do is we should notice that 4 to the 1/2 power is just 2, and 5 squared is just 25. So we have log base a of 2 minus log base a of 25. And then you should notice that these two things are subtracted, which turns into division. So we have log base a of 2 over 25. This one, again, powers or factors should be written as powers. So we have log base a of 3 to the negative 2 plus log base a of 2 cubed minus log base a of x squared plus 1. We change this addition that we have here into multiplication. So we have 2 cubed times 3 to the negative 2 minus log base a of x squared plus 1. We change this into division. We also evaluated 2 cubed and 3 to the negative 2nd power. 2 cubed is going to be 8. 3 to the negative 2nd power is going to be 1/9. So we went ahead and we wrote it as 9 in the denominator. And then x squared plus 1 gets stuck in the denominator because it's subtracted. All right, let's look at solving some logarithmic equations. So let's say we have log base 3 of 4 equals 2 times log base 3 of x. So in this case, we want to rewrite our 2 as an exponent. So we have log base 3 of x squared. And then if you notice, we have log base 3 on both sides. So we just ignore it. We have 4 equals x squared. Take square root of both sides, so we get 2 or negative 2 for x. Now, a quick reminder, the domain of logarithmic functions is positive numbers only. So you can't have 0, you can't have negatives. So you need to make sure you check for extraneous solutions when you're solving these equations. So if you actually take negative 2 and you plug it in here, we're going to have log base 3 of negative 2. Well, that's not going to be allowed, so that one is extraneous. So 2 ends up being the only solution. All right, let's look at another one. Let's say we have log base 2 of x plus 2 plus log base 2 of 1 minus x equals 1. Now, since we have multiplication, or sorry, kind of spoiled it there. Since we have addition, we can change it into multiplication. So this ends up being log base 2 of x plus 2 times 1 minus x equals 1. Anytime you're stuck with solving these, let's say you get to this point and you're just not sure what to do, one very good option is to change it into the other form. So if it's written in log form, write it as exponential. If it's written in exponential, take log of both sides. So this one, 2 is our base, okay? The 1 should be our exponent, so we have 2 to the first equals x plus 2 times 1 minus x. In order to solve this, we need to go ahead and FOIL this out. So we have 2 equals negative x squared minus x plus 2. Move everything so it's on the left-hand side so that you just have 0 on the right. This ends up being x squared plus x. The 2's cancel, so we have equals 0. And then we factor. X times x plus 1 equals 0. So we get x equals 0 or x equals negative 1. Now again, you need to check these answers. Okay, so the answer can be negative, but when you plug it in, you cannot have log of a negative number. So if we plug 0 in, we have 0 plus 2 is 2, that's fine. 1 minus 0 is 1, that's also fine. Negative 1 plus 2 is 1. 1 minus negative 1 is 2. So those are both solutions that are in the domain. So it's okay to have negative 1 as a solution. You just can't have it be negative when you actually plug it back in here. All right, let's say we have something like this, 3 to the x equals 7. So what we want to do for this one is anytime you have an x in your exponent or a y or whatever you're solving for, and you cannot write it as the same base. So for example, for this one, we cannot get 7 to look like 3 to some power. So what we need to do is we need to either take log or natural log of both sides, and that will allow us to bring our exponent out front. So I'm going to take natural log of both sides. So we have ln of 3 to the x equals ln of 7. Ln is just like any other function. You can take square root, you can square things as long as you do it to both sides. The same is true with log and natural log. Now we just take our exponent, which is our x, and move it out front. So we have x times ln 3 equals ln 7, and then divide both sides by ln of 3. So our exact answer is ln of 7 over ln of 3. Please make sure you pay attention to whether MyMathLab wants exact or approximate answers. Sometimes it wants both. So if it wants the exact answer, you're going to put in this. If it wants an approximate answer, then you're going to carefully put this into your calculator and then round. So we get 1.771. Now, if you want to check this, all you have to do is 3 to the 1.771 power. Make sure that it's close to 7. I think it's like 6.99 or something like that, very close to 7. All right, this one looks very similar to the last one, except we have kind of this extra thing here. We have a 5. So we have 5 times 2 to the x equals 3. Now, before you take natural log of both sides, what you want to do is you want to make sure that the thing that has the exponent attached that you're trying to get rid of, x in this case, or trying to get by itself, we need to get rid of whatever is attached to it. So in this case, we have 5 times. So what we want to do is we want to divide both sides by 5 to go ahead and clear that out of there. So if we divide both sides by 5, we get 2 to the x equals 3/5. And now we can go ahead and take natural log of both sides, bring our x out front, and then finally divide just like we did before. So we have x equals ln of 3/5 divided by ln of 2. Again, approximate answer, negative 0.737. You can plug this back in for x and make sure that it works. All right, now we have an even uglier one. Let's say we have 2 to the power x minus 1 equals 5 to the power 2x plus 3. Now, thankfully, we're going to go about the same kind of steps to solve this, okay? So all we have to do is just take natural log or log of both sides, doesn't matter which. That will allow us to bring our x's out front. So we take ln of both sides, and then we bring our exponents out front, so they're written as factors. Make sure you have to put parentheses around your exponents so that you don't forget to distribute. So on the left-hand side, we have the quantity x minus 1 times ln of 2 equals the quantity on the right-hand side, 2x plus 3 times ln of 5. Now, it's really important to keep in mind that ln of 2 and ln of 5 are just numbers, okay? So if you just pretend they're a 2 and a 5, you're going to treat them the same way that you would as if they were a 2 and a 5. So you want to distribute ln of 2 and ln of 5 to everything on their respective sides. So on the left-hand side, you get x ln 2 minus ln 2, because 1 times anything is just itself, equals 2x ln 5 plus 3 ln 5. Now the whole goal is to get x by itself. So what we need to do is we need to get everything that has an x attached to one side, everything else to the other side, factor out an x, and then divide. So what we've done is we've moved this 2x ln 5 over to the left-hand side by subtracting, and we've moved this negative ln 2 over to the right-hand side by adding. And then we factor out an x, so we have x times ln 2 minus 2 ln 5 equals 3 ln 5 plus ln 2. And then we divide both sides. It looks really nasty, but this is your exact answer here. You have x equals 3 times ln of 5 plus ln 2 divided by ln 2 minus 2 ln 5, which is somewhere around negative 2.186. Okay, I want to review this compound interest formula. This is from very recently. You can always go back and watch videos that go into this in a little more depth. But you should be familiar with all of the parts of this formula. A is the amount, T is the time, number of years, okay? P is your principal, R is your interest rate, and N is the number of times that you have something compounded in a year. So if we want to solve some of these problems, we don't have to go through each of these, but I want to do maybe the first two here. Let's say that we're investing $1,000 at an annual rate of 10%, which is compounded annually, semi-annually, quarterly, monthly, and daily. So we're just going to look at annually and semi-annually. So if it's compounded annually, that's just once a year. So n is just going to equal 1. So all we have to do is just plug n equals 1 into here. So we have 1,000, that's our p, times the quantity 1 plus 0.1. We don't have a power here because we just have the 1 times 1 power, which is just going to be 1. So you get $1,100 right here. Now, if you have semi-annually compounding, that means that you have something that's going to be compounded twice a year. So what you do with your interest rate is you divide it by 2 for the compounding twice, and then you raise it to the second power. And this would be multiplied by the number of years, but in this case, we just have 1 year. So we just multiply 2 times 1, which just gives us 2. So if we do this very carefully, we have 1,000 times the quantity 1 plus 0.05 squared, since 0.1 divided by 2 gives you 0.05. In your calculator, you can either plug it in all at once with parentheses, or you can do it step by step. You would do the 1 plus 0.05, hit enter, square that number, and then multiply by 1,000, and you should get $1,102.50. Now, the important thing to note is what these other n's equal. You approach the problems the exact same way. If you have quarterly compounding, that happens 4 times a year. Monthly compounding happens 12 times a year, and daily happens 365 times a year. And each time, as it's compounding more and more frequently, you're going to make more and more money. All right, so let's look at an example here. I'm just going to skip right to the 3 equations step. It would be good to maybe go back and take a second look at that from the previous week's lecture if you're confused on it. Let's look at this applied problem, and then we're going to do an equation where we have to solve for x, y, and z with 3 different equations. So a movie theater sells tickets for $8 each. Seniors receive a discount of $2. One evening, the theater took in $3,580 in revenue. X is going to represent the number of tickets sold at $8, and Y is going to represent the number of tickets sold at a discounted price of $6. We want to write an equation first that relates these variables. So if you take the $8 multiplied by the number of $8 tickets sold, and the $6 and multiply it by the number of $6 tickets sold, which is Y, and you add those two things together, what you should get is your total revenue, which is going to be $3,580. So we have this nice equation here, 8x plus 6y equals 3580. And then we also know that 525 tickets were sold. You have to be given some other piece of information like this. So in this case, we know that x plus y is going to give us our total number of tickets, which is going to be 525. And now all we have to do is just put those two things together. So we have kind of a system of equations now. We have 8x plus 6y equals 3580, and x plus y equals 525. We can either use substitution or elimination. Elimination is what we use for our 3 equations with 3 variables, so we're going to do that here. So if we multiply the bottom equation by -6, then our y's will cancel. So when we multiply the bottom equation by -6, we have -6x minus 6y equals -3150. And then we just have a big addition problem at this point. Our y's are going to cancel just like we want, okay? Something like this should always happen. Either x or y should cancel, otherwise you didn't do something correctly. 8x minus 6x is going to give us 2x, and 3580 minus 3150 gives us 430. And then we divide both sides by 2, so x is equal to 215. So what that tells us is that we sold 215 non-discounted or $8 tickets, and the remaining 310, which can be found by taking our 525 total and subtracting our 215, the remaining 310 were the senior $6 tickets. And you can check this by putting it back into the original scenario, making sure that you end up with the correct revenue and the correct number of tickets. All right, lastly, let's look at this system of linear equations where we have 3 variables and 3 equations given. So I talked about some methods for doing this last time. If you're a little rusty on that, I would suggest going back and rewatching that video. It goes through this exact same example. But what you need to remember is that you need to use 2 pairs of 2 equations. You need to use each equation once, and you need to eliminate the same variable each time. So you want to look for things like alternating signs or things that are going to go together very nicely. So if we look at, let's see, equation 1, that's this top one right here, and equation 3. If we multiply equation 3 by -2, then we're going to be able to cancel our x's. So when we multiply our equation by -2, on the bottom we get -2x plus 4y minus 6z equals -14. And then we add these 2 equations together. We get 5y minus 5z equals -10. I would always suggest putting like a star by this equation because you will use it again later. It's really important to make sure you stay organized with these. Now we used equations 1 and 3, so that means we need to use equation 2. And we also need to eliminate x again, just like we just did. So if we look at equation 2 and equation 3, if we multiply our bottom equation by 3, then our x's will cancel. So if we multiply our bottom equation by 3, we get 3x minus 6y plus 9z equals 21. Please make sure that you multiply both the left-hand side and the right-hand side by the number. And then we add these 2 equations together. So we get -4y plus 7z equals 11. And now what you'll notice is we have 2 equations that now neither of them have an x attached. So that's great. We have one with y and z, and we've used all 3 equations. So now what we do is we just put these 2 equations side by side, and we figure out how we should solve them. Now, these aren't particularly nice, but what we'll have to do is we'll have to multiply our top equation by 4 and our bottom equation by 5 in order to end up with a 20y and a -20y that will cancel. So we get 20y minus 20z equals -40, -20y plus 35z equals 55. Add our equations together, and we get 15z equals 15, so z equals 1. And then you just use back substitution, so you use one of the starred equations, the ones that I told you guys to put stars by, use one of those to solve. So we have 5y minus 5z equals -10, plug 1 in for z. So we have 5y minus 5 equals -10, so y equals -1. And then what you want to do is use any of the original equations, so any of these top 3, substitute the z and the y in, and get x. So if we use this third equation, we have x minus 2 times -1, because that's our value for y, plus 3 times 1, because that's our value for z, equals 7. So we get x equals 2. So our solution is 2, -1, 1. It's written as x, y,